Okay, hi everyone. This is a new video format that I'm trying out here. Um, for some of the examples that we're going to do in class, there will be a lot of writing, and getting that all on the whiteboard is somewhat challenging and probably just not a super great format. So I think instead we're going to do some of these videos using this application, which is OneNote. This is also the first of the supplements that I'll be recording. The supplements are going to be videos that are related to the material that we cover in class or are useful examples to help your understanding, but aren't necessarily essential to the main narrative. So, in this supplement, I want to talk about the chemical potential and do an example that hopefully complements the examples that we did in the main videos. So, you'll remember that the chemical potential, let's get a little bit thinner. The chemical potential mu is defined to be equal to the negative of the temperature times the partial derivative of the entropy with respect to the particle number. And we also did the derivation of what this quantity is for the ideal gas, but let's repeat that here. So we remember the Sackur-Tetroda equation says that S is equal to, well, it's N Kb times the log of sigma V over N U over N to the power of 3 halves. Then we need to add on our 5 halves N Kb. And let's just redo the calculation here. So this implies, what's going on here? Very strange. All right, well, in any case, this implies that the partial of S with respect to N is going to be equal to, first we need to take um, the product rule on the first term. That gives us Kb log sigma V over N, U over N to the 3 halves. Then, I should say we get minus the derivative nkb times the derivative of the log, which is just 5 halves 1 over n. And we see immediately that we get a cancellation there. Next, we take the derivative of the second term, which is just 5 halves kb. And this gives us another cancellation, wherein this term cancels with that term. Good. All of this then implies that mu is equal to minus kbt log sigma v over n u over n to the 3 halves. And that's it. Now, I think that this equation or this expression is fine, but we can make it a little bit more useful if we put it all in terms of t. You'll notice right now we have kind of too many variables. We have t here, we have v here, we have n here, and we have u here. So we're using 4 variables, even though we know the system's states can be described by 3. So let's figure out that. What is going on? Go down a little bit. Let's figure out that for how to get rid of that 4th variable. So I think here what we'll do is get rid of u in favor of t. So we remember that u is equal to 3 halves n kbt. And so we can pretty easily make that substitution. So we'll get minus kbt times the log of sigma v over n times 3 halves kbt, and then all of that to the 3 halves. Awesome. Okay, now let me figure out how to go down a bit. Nope. Maybe if I just go down a little and then make a mark. That might work. really does not want to work today. Okay, so next, let's think about two systems of which we're going to take. Let me make sure that this is clear that we're doing a different thing now. We're going to take two systems and do a chemical join on them. We're going to take these two systems which both have temperature T, but might in principle have different volumes, V1 and V2. And we'll use 1 and 2 as subscripts today, just to make our lives easier. Now this one is going to have N1, and this will have N2 particles. And now we'll do the chemical join. The key here is to recognize that we know that the chemical join is going to have, or maybe I should say the chemical join is going to set mu1 equal to mu2 after the join. So maybe I should give these primed symbols here. Okay, now let's do it. So mu1 prime is equal to mu2 prime is going to tell us the following. Minus, so maybe I'll write it like this, mu1 prime equals mu2 prime if and only if minus kBT log sigma V1 over N1 times 3 halves kBT to the 3 halves is equal to minus kBT log of sigma V1 over, V2 over N2 3 halves kBT to the 3 halves. Now we'll see in the next lecture that it actually is important that these two gases are the same species. So we have N1 particles in the first box and N2 in the second box, but it's the same type of gas in both boxes. That makes all of this a little bit simpler. All right, now that we have this expression, we can do a little bit more with it. So again, let me give us some more space and see if I can get OneNote to work in the way that I'd like. There we go. All right, so now we can take this expression and reduce it significantly. We see pretty clearly that kBT cancels on both sides. It was very helpful that the two boxes had the same temperature to begin with. Then we can take both sides and exponentiate them to eliminate the logs. After we do that, we can start canceling on the interior of the logs. We see that sigma cancels on both sides in particular, and 3 halves kBT to the 3 halves also cancels on both sides. So when all is said and done, we get V1 over N1 is equal to V2 over N2. Good. Okay, so now we can start to actually solve this. And I apologize. I should have been putting primes here on these ends because these are the ends after the join. Okay. Now, I think it will be a little bit easier if we actually invert this equation. So we'll go N1 prime over V1 is equal to N2 prime over V2. So this is going to be one of the equations that we need. The second one is our constraint. Which is that N1 plus N2 is equal to N1 prime plus N2 prime. So notice now that we have a linear system of equations. The first two equations are, the first equation is going to be this one, and the second equation is going to be this one. And with these two together, we can pretty simply solve. Sorry, now I need to do this again to make sure that we have enough space. Okay, so combining these two equations, we can use, for instance, substitution. So let's take this equation and say that either side is equal to n total. Then let's substitute n for n2 prime so that n2 prime becomes n total minus n1. That would give us that n1 prime over v1, and I'm being a little bit cavalier here, is equal to n total minus n1 prime over v2. Now I can move this n1 prime to the other side, and that would give me 1 over v1 plus 1 over v2 times n1 prime is equal to n total over v2. All right, let's keep going with this. So we're going to need to combine the denominators in this term in order to make this make more sense, or to be able to work with it more easily. So common denominator is going to be v1 times v2, and we'll get v1 plus v2, or v total, in the numerator. So this will be v total over v1 v2, and 1 prime is equal to n total, oops, this should have been implies, is equal to n total over v2. And we see that a v2 cancels on both sides now. Okay, we're almost home free. Now to solve for n1, we just need to multiply v1 over v total on both sides. And this equation is our final answer and should seem pretty familiar from some of the other examples that we've done. So the box on the left, box 1, receives particles after the join in proportion to its volume. Since the temperatures and therefore the energies are equal, the only thing that differs between the two boxes, or the only things I should say, are the particle number and the volume. And since we're going to fix the particle number to some new value with the chemical join, only the volumes can really determine that. So let me just make a note of what we found. So box 1 gets particle number in proportion to its fraction of volume. Okay, before I end the video, I just want to sort of reiterate the whole point here. Doing this calculation by first finding both of the entropies and then maximizing them with respect to n1 prime by making a substitution for n2 prime in terms of n total and n1 prime would be very time consuming. Chemical join here allowed us to do this calculation in just a few lines. So in general, remember that these join operations become much easier when we use the intensive variables. And with that, I'll say thank you so much for watching, and I'll see you in the next one.